protocol and the procedure and the common questions which you get in the exam. So in this webinar, for the first 45 minutes, we'll discuss some concepts. I'll just share my screen, 1 second. Yes, can you see the screen? Okay, I hope so. So, in this, we'll be discussing the alternative to practical skills. Okay. In the chemistry lab, when you enter into a chemistry lab, you see a different equipment, different apparatus, which some are used to measure the temperature, some are used to measure the time, some are used to measure the melting point, boiling point, or the amount of heat, or the melting point, boiling point. These are the measuring apparatus. You have a measuring, this is a beaker, we call it conical flask, or it's also called as Erlenmeyer flask, conical flask or Erlenmeyer flask, and this is a volumetric flask. They're all used to make some quantitative measurements, measuring the amount of liquids. We measure different liquids, the quantity of liquids using different, according to our convenience. Some in some titration experiments, you use burette, pipette, and some volumetric analysis, you use volumetric flask, and all this apparatus. Now, in this, we will be discussing some experiments, how to do these experiments. See, as you can see here, let us discuss the first experiment. How to reduce copper oxide to copper. Do you know copper oxide is different from copper? Copper is a shining brown metal, right? Have you seen copper metal? Amelia and Aish?
Yes.
Okay, what is the color of copper metal?
I think copper metal is like brownish, whereas copper oxide is like black.
Very good. Yeah. You know something? Copper and gold are the only two metals which are non-silvery white. All the other metals are silvery white, like silver, platinum, aluminum, iron, all metals, chromium, all metals are the same color, silvery white. But gold and copper are the only two metals which are non-silvery white. Metals, I talk about metals, non-silvery white. And of course, as you said, right, copper is nice shining brown metal. But that's a fresh copper. When you can see the copper in the wire. Take some copper wire, just hold it with a forceps and burn it in flame. When you burn, we call combustion. In chemistry, burning is called combustion. Reacting with oxygen is called combustion. So when you take a copper wire and burn it in oxygen, it turns black. Black, that is copper oxide. I'll write here the equation. This is copper, and when you heat it, react with oxygen, you get black copper oxide. Black copper oxide. That's why, when there is a short circuit, the entire the electrical equipment, the wiring, it turns black because of the short circuit, because of the fire. The copper wire gets heated up in the air and turns to black copper oxide. Now I want you to take that copper oxide. Take that copper oxide, put it in a glass tube, close it with a one-hole cork, and insert an open tube. Open tube is just something like an open tube. I mean, it's a glass tube open at both the ends. It's open at both the ends. Insert it. Now heat this copper oxide from outside. Heat it from outside. You know what happens when you heat this copper oxide from outside? When you heat this copper oxide from outside, you know what happens? This copper oxide, it gets reduced to copper. Can you tell me, Ayush or Emilia, what do you mean by reduction? What do you mean by reduction? What is meant by reduction? Is it loss of oxygen or gain of oxygen?
It is loss of oxygen.
Very good. Here, this copper oxide is losing oxygens. or it's giving oxygens to methane and getting reduced to copper. So this is a reduction reaction. And this copper, it donates oxygen to methane. So when this methane gets oxygen, all the carbon is oxidized to carbon dioxide, and all the hydrogen part is oxidized to water. Not only methane, take any hydrocarbon. Since it has carbon and hydrogen, all the carbon is oxidized to carbon dioxide and the hydrogen is oxidized to water. So you have the carbon oxidizing to carbon dioxide, that is oxidation, and the hydrogen is also getting oxidized to water. So you can call that this reaction is a redox reaction. So when you do an experiment, you come across various concepts. Here you understand what is combustion, what is burning, what is reduction, what is oxidation, what is redox reaction. So what is a redox reaction? Yes, Aish, you have any question?
Yes, I wanted to ask. Okay, so first of all, you asked what is a redox reaction. So redox reaction is basically a reaction where reduction and oxidation happen simultaneously. And one question I had was that why is methane specifically used in this experiment?
Not only methane, you can even use ethane, propane, butane, anything. I just took some hydrocarbon.
Oh, okay, so it just has to be a hydrocarbon then.
Yeah, it can be anything. Yeah. Okay. You can even simply take hydrogen, just hydrogen. That's it. This hydrogen will become H2O.
Oh, okay, got it.
Yeah, you can take ethane, which is C2H6, anything. Yeah. Okay, right. Now, so you can see, as you said, very good. I'm so happy. Yeah, because this is a redox reaction where reduction and oxidation both happen simultaneously. Now I'll just explain. I'll walk you through a real-time activity. But I'll just tell something. How do you know that you are getting this? How do you know that the products are methane, water and carbon dioxide? How do you know? We will discuss that here. I mean, how do you know that carbon dioxide is produced and water vapor is produced? This is water vapor, because carbon dioxide and water vapor both have no smell, both have no color, both have no taste. Then how do you identify? I'll tell you that test for carbon dioxide and water in the next activity. Now here, look at this activity. Here the same thing. I'm trying to do combustion of any hydrocarbon. Emilia, you said why only methane? You can take ethane, propane, butane, any hydrocarbon. And how do you get an hydrocarbon? I'll just take some candle flame or a spirit lamp or a wax candle and burn it. When I burn, these hydrocarbons are oxidized, and that is called combustion. Remember, in chemistry, combustion means reacting with oxygen, burning with oxygen. For example, let's take a substance, a reactant X. When I'm doing combustion of oxygen, it means I'm burning. See, burning is a common name, but combustion is a technical name in chemistry. Both are synonymous, both are same. But actual chemical meaning is that when you do combustion, you're actually burning it with oxygen and you get some product. Why? With release of heat. Heat is also released. If there is no heat released, then that's just an oxidation reaction. But if there is also heat released, we call it combustion. So you should understand the difference between a general oxidation and a combustion. All combustions are oxidations, but all oxidations are not combustions. Because for combustion of any substance, you have to heat it with oxygen, react with oxygen, burn it with oxygen, and you get some products, blah, blah, Y, Z, X, something. But you also get accompanied with heat. Heat is also released. So all combustion reactions are exothermic reactions. But here, my reactant X is some hydrocarbon. It could be methane, CH4, or ethane, C2H6, or propane, C3H8, anything. Let's assume that this hydrocarbon, when it is burning, this is methane. Let's say methane or wax. It's just wax, because that's a wax candle. And when this wax is burning, it's actually reacting with oxygen and producing two products. Can anyone tell me what are those two products obtained by combustion of wax? What are those two products? Can anyone? Wax is a hydrocarbon. And I told you, when any hydrocarbon is undergoing combustion, you get two substances. What are they?
Carbon dioxide and water.
Very good. Good. Keep it up. Because hydrocarbon is having hydrogen and carbon. The name itself tells you. And when you're burning it, all the carbon gets oxidized to CO2 and all the hydrogen gets converted to H2O. Now you have a mixture of H2O and CO2 as the products. Now these products, they pass through this tube. I have two test tubes connected by a funnel and a bent tube, and both are having a two-hole cork. And this is a setup. And in one of the test tube, I have kept a cobalt chloride. Cobalt chloride is a blue color salt, and cobalt chloride is a blue color paper. You know, when cobalt chloride comes in contact with water, it turns to a beautiful pink color. That is a test to identify water as a liquid, or water as a water vapor, or even ice, anything. Okay, so cobalt chloride is used to test water. So when these products are passing through the first tube, this water turns cobalt chloride to pink color. It turns to pink. This indicates that one of the product is water. But this carbon dioxide goes left unreacted into the next tube, into lime water. Can anyone tell me what is the formula of lime water? What is the formula of lime water? Any idea? Okay, don't worry. It is calcium hydroxide. Chemical name of lime water is calcium hydroxide. Okay, when this carbon dioxide is bubbled through lime water, it turns to milky white color. It turns to, actually, you get calcium carbonate, which is an insoluble precipitate, and that gives it a white turbidity, white precipitate. So as long as you pass carbon dioxide, you can just take a glass, pour some lime water, put a glass tube or some pen or a refill or something like this, you know, just take, this is a pen, I just blow some air through it, because you exhale out carbon dioxide, the lime water turns milky white. Now I'll just show you a real-time experiment of what's actually happening. Just a second. Okay, right. Now can you all see this? See here, this is the test to detect water by using cobalt chloride paper. This is the blue cobalt chloride paper. See, when I dipped in water, it turned to pink. Or this is hot water and there is some water vapor coming up. There is some steam on the top. So when I expose this blue copper chloride paper to steam, you can see that, let me fast forward it. It slowly turns to, it fades to pink color. It turns to pink color. Or you just sprinkle some water on it. It turns to pink color. You can just see here, it turns to pink color. It turns to pink. Now let us use this copper chloride and this test in our actual experiment. Yeah. Now look at here. This is the setup. I have a conical flask. I have two test tubes, and this is a setup. Here you have calcium chloride paper, and I have lime water here. Oh, let me write. This is cobalt chloride, COCl2. I'll write the color, COCl2. And this is lime water, calcium hydroxide. Now I start my experiment. Here, okay, this is lime water, calcium hydroxide. I'll just fast forward it. This is a cobalt chloride paper. I'll just stick one cobalt chloride paper so that I can take it as a reference to observe the change in color. And this is my wax candle, a source of hydrocarbon. A source of hydrocarbon is my wax candle. And I start burning my wax candle, a hydrocarbon. So definitely I get carbon dioxide gas. Oh, and I connect a pump here, a vacuum pump, because this vacuum pump sucks the air from this right tube, and that will suck all the air from the first tube, and that will suck the gas. here. I mean, there's a suction pressure created. So you have a current of air passing through the entire setup. So there's just some vacuum pump. And I'll also connect a timer to see how much time it has taken to observe the change in color and of the cobalt chloride, change in color of calcium hydroxide. I'll just see here. So this is actually what's happening. I'm burning my wax candle. And when I'm burning, I get two things here. I get carbon dioxide and water, two things. And as this both carbon dioxide and water pass, what happens is you can see this carbon dioxide is bubbled here. You can see it turning milky white. That's a very famous test for carbon dioxide. Remember, you might be asked in your practical exam, what is the test for carbon dioxide? Simple. When carbon dioxide is passed through lime water, it turns milky white. And they may ask you, what is the reason? Because, can anyone tell me what is the reason? Why does it turn milky white? Why does this lime water turn milky white?
Because it comes in contact with carbon dioxide.
Very good. It comes in contact with carbon dioxide. And when it comes in carbon dioxide, what do you get? So don't worry, I'll tell you. So this is, oh, stop sharing. Yeah. So, okay, this is calcium hydroxide. When it comes in contact with carbon dioxide, they both react. And when they both react, I get calcium carbonate. And you know, all carbonates are insoluble in water. So the calcium carbonate is also insoluble. You get precipitates of calcium carbonate here. That gives it a white turbidity because of the suspended calcium carbonate molecules. That's white color. Okay, and look at here. The blue color paper has already turned pink color. That is a test for water. So you have learned two tests. Test for water by using cobalt chloride paper and test for carbon dioxide by using calcium hydroxide. Is that clear? Am I making sense?
Yes.
Okay, great. Thank you. Now, let's go with the next activity. Okay, now this is another experiment. Here, this is an experiment to prove that rusting of iron requires both oxygen and water. You know what is rust? If you look at a fresh iron, a new iron nail, it's nice shining gray color, isn't it? Or even sometimes silvery white color, fresh iron. But when you leave this iron nail exposed to moist air, or commonly in rainy seasons, all the iron benches and iron articles, they undergo rusting. But what is rust? Do you know what is chemically, what is rust? Okay, I'll help you. Rust is, this is iron. This is nice shining white or shining gray. But when I expose it to moist air, when I say moist air, there is moisture in the air and there is oxygen. This is our moist air, not dry air. Remember, not like in summer season. It's a rainy season or winter season. Moist air. There is moisture, a lot of humidity, and also oxygen. Air has 21% oxygen. Now, when they both undergo reaction, it's a slow process. You get rust. And what is that rust? Rust is ferric oxide, hydrated ferric oxide, XH2O. XH2O. This is rust. Fe2O3 is called as ferric oxide. That's not rust. Just Fe2O3 is not rust. It's just a brown product. But hydrated ferric oxide is rust. So now, students, tell me, what are the two requirements for rusting? What do you require for rusting? What are the two requirements for rusting? There are two requirements. Any guess?
Water and moisture.
Very good. No, water is already moisture. Water and oxygen.
Sorry.
Okay, no problem. Now let's do it as by small activity. I'm going to take 3 test tubes and label them as A, B, C, and I'll drop an iron nail into the 3 test tubes. And in the first test tube, I'll add the normal tap water because tap water has a lot of dissolved oxygen. So I'll pour normal tap water to half of the length of the nail and close it with a cork. And the second test tube, I take boiling water, because when you boil water, all oxygen get escaped. You get oxygen free water. So I take the boiling water. Remember, boiling water has no oxygen, just H2O, just water. I pour it in the test tube until the nail is completely immersed. And then I add some oil onto the top, because the oil will seal the top layer. It blocks the entry of oxygen. So you have only water, no oxygen. And in the third test tube, I take anhydrous calcium chloride. Anhydrous calcium chloride is a hygroscopic salt. Hygroscopic salt means which absorbs moisture. Calcium chloride is the best hygroscopic salt. I add it in this, about 5 to 10 grams I add in this. And it absorbs all the moisture. I'll close the 3 test tube with one whole cork, with a cork, not a whole cork, just a cork. Here, in this third test tube, if there is any trace of moisture, all that is absorbed by the anhydrous calcium chloride. So what I have here is only dry air, no H2O, because all the H2O has been absorbed, no H2O. And here there is no oxygen. I have only water here. But here I have oxygen dissolved in the water. I have water, and also the air has oxygen. So there are all the requirements. Now, can you tell me in which test tube you have rust, in A or B or C? In which test tube you find rusting? Come on, I think you might be knowing. It's so easy.
A.
Yeah, good. A. Other people also, Emilia, Jeremiah, please respond. So you find, because you have both water and oxygen. The same activity, I'll again walk you through an animation, through a real-time video. Just look at this. Oh, this was a previous experiment. Okay, now look at here. Now, here I have 3 test tubes. These are all the requirements, not required, Okay, I've taken 3 test tubes, A, B, C, and I've added an iron nail in each of them. And in the first test tube, I'm adding some tap water to half the length of the nail and closing with a cork. And in the second test tube B, I'm adding hot water, boiled water, until the nail is completely immersed, because the boiled water is free of oxygen, no dissolved oxygen. We say DO, dissolved oxygen is absent. And I slowly pour some oil, so that the oil, it has less density than water. It floats on the top as a layer, blocking the entry of any oxygen. So there is no oxygen, only water here. And in the third test tube C, I add some anhydrous calcium chloride, hygroscopic salt, and close it with a cork and leave it for a few days, maybe 3 days. And then you come and see. You see that in the first test tube, you see rust. The hydrated ferric oxide, you can see as a reddish brown sticky deposit on the iron nail. But B, there is no rust here. Can anyone tell me why there is no rust in the second test tube B? Why there is no rust? Jeremiah, Emilia, Aish, why there is no rust in the second test tube B? Yeah, Aish?
Because there is oil in it, so that kind of obstructs like the
Yeah, very good. Fatima, yes, good. There is no oxygen, only water, so there's no question of resting. Now let's look at the third test tube C. Even here there is no rust, but what is the reason? Fatima and other participants, it would be great if you can share a response. Okay, because there is no moisture, you have only oxygen, so there is no rusting. Okay, you should understand how you need to study an experiment, understand an activity, and what kind of questions you come across in that experiment. Okay, now Okay, let's go back to the next activity here. Now, this is an experiment to prove that air has 21% of oxygen. Okay, you know, air is a mixture of various gases, but the most important gases which are in the largest proportion. Tell me, which gas is highest in air? Which gas? The highest percentage by volume is which gas in the air? Yes, Ayush.
Nitrogen.
Very good. 78% is nitrogen. Okay. And next highest volume is which gas? Second one. That is what we are going to study now. 21% of oxygen. And then carbon dioxide is 0.03%. Participants, you please remember this. You may come across in your practical, a lot of questions have come in the past papers about the proportion, the percentage of these gases. Remember at least these three gases. 78% is nitrogen, 21% is oxygen, 0.03% is carbon dioxide, and the rest is all other gases, inert gases and like that. But in this activity, we're going to prove that air has 21% of oxygen. Now, how do you do this activity? Take two syringes, okay, and connect them by a glass tube. When I say open glass tube, it's open at both the ends. The nozzle of one syringe is connected to one end of the tube, and the nozzle of the other syringe is connected to the other end of the tube. But this tube at the middle, it has nice shining brown copper, not copper oxide, copper, fresh copper. And now take some air, just move the piston out, about 100 ml of air. Take exactly 100 ml of air. Okay. And now you start heating this copper from the bottom and simultaneously pull and push this right side syringe piston out and in, out and in, out and in. When you push out and in, what happens is the air, the 100 ml of air on the left syringe moves from that syringe across the tube through the copper, because it's a wire, it can pass through the wire, and move into the right side syringe. And when you press in the piston, the air again moves to the left side. So keep doing this for some time until the entire copper is burnt, undergoes combustion to black copper oxide. Just move the air left and right, right and left, left and right, right and left. Keep doing it for some time until the entire copper turns to copper oxide. But after some time, after the entire copper has turned to black copper oxide, there will be no more change in the volume. You can see that this final volume is only 78 to 79 ml. Then what happened to the remaining 21 to 22 ml of air? Are you understanding? You have taken 100 ml of air, and finally you're left with only 78 to 79 ml of air. What happened to the remaining 21 ml of air? It is reacting with copper, because oxygen is the only gas here which reacts with copper. So I'll write here. So when I'm taking copper here, that combines with oxygen and forms this black copper oxide. This is copper oxide. And what percentage of oxygen has reacted with copper? 21%, because we are taking out of 100 ml, it's 21 ml. So you'll understand much better when I show a real activity here. Stop sharing. I'll stop my virtual whiteboard because I want to show real experiment here. Now, see, I have a syringe here. This is a syringe. It's a 100 ml syringe, and I have taken another syringe. So there are two syringes here, and I'm connecting these two syringes by a glass tube. I've just taken a pen. It's a glass tube, and inside this glass tube, I'll insert some copper wire. Just take some fine copper wire and insert it with some small needle until the middle of this tube. Now connect one end with a syringe, and the other end also you connect it with another syringe, like this. Okay. Now, after connecting it, what you do is heat this copper from the bottom, and as you start heating, start pulling and pushing this test tube, I mean this syringe. First you have taken 100 ml, take 100 ml like this. You know, here this is 100 ml, but this 0 ml here, there is no ml here, no air here, but this is 100 ml of air. Now press this. There is actually some gap here, but when you press, what happens is all this 100 ml of air passes through this tube into this syringe, and again pull it out. The air again passes into this syringe, and again press it inside. Again the air passes into this syringe. So keep swapping this air left to right, right to left for some time until this entire copper turns black copper oxide. And finally, after doing like that, you know, if you check here, the volume of air will be left only 78 to 79 ml of air. What happened to the remaining 21 to 22 ml? It has reacted with oxygen, and that 21 to 22 ml of air is not air, it's oxygen. So this proves that air has about 21 to 22 or 21% of oxygen. So I'll just show you the real experiment here also. Just a second. Right now, previous this was the activity. Now I'll just make it fast forward. So this is a setting here. Now here you are actually heating this. You know, initially you have taken 100 ml of air in this syringe, but there is no air on the. So look at here. This is 100 ml of air. This is initially 100 ml of air, but here it's 0 ml. There is no air here. Okay, and now as you pass, what happens as you pull and push this piston across this tube? What happens here? So you can see it as you press. See, the syringe is going outside here, and then again pull it. Again pull it. So I'll just fast forward it. You do it for some time until the entire copper becomes copper oxide. Copper oxide. And do it and do it and do it and do it. Finally, you'll be left with only 78 to 79 ml of air here. This is only 78 to 79 ml of air. This one. So this shows that 21 ml of air, which is not air, which is oxygen, has reacted with copper. So this shows that air has 21% of oxygen. Is that clear? Am I making any sense? Okay, great. Now, let's again go back to our Tutopiya resource. Okay, right. Now, these are also other reactions, other experiments. I'll just discuss any other easier one. Yeah, we'll discuss chromatography. Okay, you know, because the chromatography is a very easy experiment, commonly conducted, commonly asked in the lab. It's easy to conduct with the cheap materials, easily available materials. You can do it. You may ask you to do the chromatography of ink, or chromatography of a chlorophyll extract, or chromatography of blood, or chromatography of saliva, or any sample, any liquid. You can do chromatography. But what's actually meant by chromatography? Do you know what is chromatography? Chromatography is a technique used to separate the components in a liquid. Because when I take, for example, let's take ink. You know, I have a marker. This marker, when I squeeze, I get the marker drop, ink. But that ink, it may be black color. It's black, but it may have various compounds with different colors. It may be a mixture of various other components. How to separate these components in a liquid mixture? You do it by a chromatography. Remember, in a chromatography, I'll just show it on a whiteboard better. Yeah. See, look at here. I'll teach you a simple. Emilia, can you mute your mic? Emilia? Okay, anyhow. So I'm going to take a beaker, and I'll take some water in that beaker, and I'm going to take a filter paper, which is called filter paper, or you can call it's a stationary phase, or I can take a blotting paper, or I can take a chromatogram, or you can take a tissue paper. or a newspaper, anything which can absorb a liquid. Take such paper, take a paper, and this is a paper, and this paper, draw with a marker. I could have made this before itself. Take a paper like this, okay, from 2 centimeters above the bottom, draw a marker, draw a line like this with a marker, draw a line, and stick this paper to a pen or a pencil and keep it in that glass. But take care that this marker should be above the water level. Okay, do not take water to so much. I'll take water a little, only little up till here. Okay, wait 1 second. Yeah, this is the water. And now what I'm going to take, I'm going to put this tissue paper or the chromatogram or chromatography paper inside this. You even get ready-made chromatography papers which are called chromatogram. Chromatogram or chromatography paper is the same thing. Okay, now I'm going to put this in this here. So what happens? I suspend it with a pencil here, and this is my paper. The paper has to be just dipped in the water level, but you take care that your ink, the marker line is just above the water level. It's here. Okay, your ink line should be above. If it's about to dip inside the water, remove some water or fold this paper here. Okay, and you leave this for about 1 or 2 hours. All this water is absorbed by the paper and it passes through the ink line and goes up. As this water moves through the ink line, it separates the various components in that ink. You know, like for example, imagine you have thrown some marbles. You have some marbles of different size. You have 3 sizes of marble. You have a bigger marbles, smaller marbles, and still smaller marbles. Okay, 3 sizes: big one, medium one, and smaller one. And all these marbles are scattered on the floor What you do is now try to flush some water. When you flush some water, what happens? You know, this water, it will push the heavier molecules forward or the lighter molecules forward. Which one? Can you tell me the answer? Did you understand my activity? You have taken marbles of different weight, different size, and you have scattered them on the floor. And take a bucket of water and gently flush them, throw them against the marbles. This water will push the heavier marbles forward or the lighter marbles forward easily. Can you tell me, Emilia, Aish, Jeremiah, Abdullah, Fatima?
Wouldn't it move the lighter marbles forward?
Very good, lighter molecules. Good, because they're light. Here also, in this ink, you have different molecules of different molecular weight, but the ones with lesser molecular weight are pushed by this mobile phase, which is the water, forward by greater distance. But the heavier molecules with a heavier molecular weight are also pushed, but slowly. So you have maybe this ink is having 3 types of molecules. The smaller molecules are here, and maybe the heavier molecules are here, and maybe the heavier molecules are here. So you get 3 bands or 3 lines like that you're separating. But what's more, from your IGCSE practical point of view, is that they ask you, what are the 3 essential requirements of conducting a chromatography experiment? There are 3 things here, which is called the stationary phase, because the paper is not moving. It's stationary. We call it stationary phase. Okay, or you also call it as a chromatogram. You know, chromatogram can be a gel, or it could be a paper, or it could be a solid. It could be anything. There are different types. You have gel chromatography, paper chromatography, solid chromatography. Here we are taking a paper chromatography. The paper is not moving. It's stationary. It's called a stationary phase. And the second one is the mobile phase. Mobile meaning which is moving. Here the water is moving. It's called the mobile phase. It could be water, or sometimes they commonly take a sodium hydrogen carbonate, which is also called baking soda. Take some baking soda, a pinch of baking soda, mix it in water, and that's your baking soda solution. Add it into this. Even that runs through the paper. And the other one is our test ingredient, the test substance or the solute. The solute. This is our solute. This also we require. This is a solute. Okay, it should be soluble in that water. It should be soluble in that mobile phase or in the sodium hydrogen carbonate. Okay, you'll understand it better when I show you the real-time activity for this also. Just a second. Yes. Oh, this is a different one. Yes, it's a long. I'll just walk you fastly. I have three test solutions. I have three solutes. One is the unknown, one is the blue, one is the black, one is the red, and one is the yellow. Okay, and I'm going to take a chromatography paper, or it's also called chromatogram, a pencil and a scale and all these things. See, this is our mobile phase, the moving phase, which is sodium hydrogen carbonate. I told you can even take water, but here we are going to take the mobile phase is sodium hydrogen carbonate. And these are the capillary tubes just to take them. Now I take my tissue paper or the chromatography paper. I draw a line about 2 centimeters above, from the bottom. I draw a line. It's a pencil. You need not take a marker line, because I'm going to use a different solute to test. So this is just a pencil line about 2 centimeters from the bottom. And now what I do is with a capillary tube, I'm going to take a drop of this yellow stain, yellow dye, and put one drop there. And with a different one, I'm going to take a black one and put another drop. So I'm going to test these 4 solutes. So red one. And next we have our unknown one, the unknown one. Okay, that is also another test solute. So I have 4 solutes. So I'm going to perform the chromatography of these 4 solutes. Now what I do is I put this paper, I take some sodium hydrogen carbonate, which is my mobile phase, and I take some paper slip, and I put a paper clip. But before immersing it, test it. Does the water level go above the line or below the line? Test it. Don't dip it. You keep it outside. Keep it outside and see the level. Is it above? Oh, it's going to dip into this. So what I'll do is you can remove some liquid, or you can fold this paper. Make a fold. So I'll make a fold, one more fold like this. One more fold, and just see. Oh, it's gonna dip again. So maybe I'll remove some more liquid or make another fold. And now clip it and leave it for a couple of hours. So you can see here the water level, the solvent. The solvent is slowly moving up. It's slowly being absorbed. It's absorbed. And at this point, let me write the 3 substances which are very, very important for your a practical exam. Here you have this is called this is sodium hydrogen carbonate. What is the sodium hydrogen carbonate? It is a solvent. And this solvent, is it a stationary phase or a mobile phase? Can anyone tell me? This liquid sodium hydrogen carbonate, is it a stationary phase or a mobile phase? It's moving, getting absorbed by the paper. So what it is it a stationary or mobile phase?
Mobile.
Very good, Abdullah. Mobile phase. Good. See, good. Mobile phase. Okay. And the paper is not moving. So what do we call the paper as? What phase? I call it simply chromatography paper. I call it chromatography paper, or I can call it simply as a chromatogram. Okay. And what is it? Is it what phase I call it? What phase? It's not moving. So what phase is it?
Stationary.
Very good. Yes. Stationary phase. Good. And now this is our test solute, which we are going to test. How many substances are there and what is their molecular weight? We can even find the molecular weight. I'll tell you how. So this is the test solute. Okay, now I'm continuing my experiment. So what happens? Slowly, you can see slowly the substances are moving. Can you see? Slowly they are moving. Okay, actually I paused it because this is a long experiment, but here at this point of time you will know the water level, how much distance it has moved. Now carefully look everyone, all of you, what is the length to which this water level or the solvent has moved. Let us suppose I'm taking in a time of something like 1 hour. In 1 hour, this water has been, or the sodium hydrogen carbonate, it has moved by a distance of let's say 8 centimeters. But the blue solute has moved, this is our solvent. Wait, this is my solvent, which is sodium hydrogen carbonate, which has moved by 8 centimeters. And now my first test solute, which is the blue stain, it has moved by, let's say, 4 centimeters. That is the solute. When you know these two parameters, you can calculate something called as RF. What is RF? RF means it is the retardation factor. Okay, I'll write here. We call it as retardation factor. RF. How do you calculate the RF? Retardation factor of what? It is the retardation factor of that solute, of the first one. Okay, of the yellow stain. How do I know it? There's a formula for this. The formula is distance traveled by the solute. Distance traveled by the solute over distance traveled by the solvent in the same interval of time, in the same 1 hour gap. Now, participants, can anyone tell me what is the retardation factor of this yellow stain? What? Emilia? Ayush, Abdullah, Jeremiah, Fatima, can you tell me what is the retardation factor of the yellow stain? Simple. What is the distance moved by the solute? I mean, the solute is my the first one, yellow, which is 4 centimeters. 4 centimeters divided by what is the distance traveled by the solvent? What is it?
8 centimeters.
Very good. 8 centimeters. And that would give you 1 by 2, which is 0.5. It has no units, just a number. No units, just a number. Retardation factor is 0.5. Now, I'll ask you a small question. If this last stain, the black stain, it has moved by only 3 centimeters, then what is the retardation factor of the black stain? Can you tell me?
Yes.
Come again, Fang? What is the retardation factor of the last stain, the black stain? I gave you a hint. The distance traveled by that solute in the same 1 hour is only 3 centimeters. So can you calculate now?
0.375.
Okay, very good. How did you get it?
By dividing 3 with 8.
Yeah. I mean, tell me the fraction. What by what?
3 divided by 8.
No, very good. Correct. Good. That's right. 3 divided by 8. Correct. And you can do the maths because I don't have a calculator. 3 divided by 8, whatever it is. That is your retardation factor. So now, did you understand how to find the retardation factor? You might be giving an experimental image and you might be giving the distance moved by the, you can see the water level, I mean the solvent level, you can measure it with a scale, and also the stain. Okay, now now so we are running out of time. We'll just do a small quiz. We'll do a quiz. I actually wanted to discuss a few more experiments, but I'll just wind up with a small quiz. Just a second. Yeah. Now, can you answer the first one? The question is, lime water. I told you lime water is calcium hydroxide. A white precipitate is formed when carbon dioxide reacts with lime water, turning it milky white. When lime water turns milky white, what is the formula of calcium hydroxide? I explained this in the test for carbon dioxide. Can anyone try? See, based on the experiments we have conducted, we have studied, I taught you how to learn and how to understand experiments, because from those experiments you get this type of questions. You may get some questions from the procedure of the experiment. You may get some questions from the precautions of the experiment. You may get some questions from the conclusion of the experiment, from the aim of the experiment, different questions. So you have to understand the essence of the experiment. Here, tell me what is the answer. I have taken calcium hydroxide. The formula is CaOH taken twice. And when I pass carbon dioxide gas, what do I get? I get water. But what's more important is you get an insoluble salt. What is that salt? I get a white precipitate of some salt. White precipitate of some salt. What is that salt? Can anyone tell me? That is your answer. What is that? Abdullah, maybe you can try.
CaCO3.
Very good. Good. Keep it up. I get CaCO3 because I told you all carbonates are insoluble. Calcium carbonate, magnesium carbonate, they're insoluble in water. So when you dissolve in water, you get some white precipitates. Okay, good. The first one. Next, I'll lock it. We'll just do three questions, and then our coordinator would have a word with you all. The second one, yeah, slaked lime is formed when calcium oxide is formed from calcium hydroxide. How? You have to, you are given a word equation, and you have to write the skeleton, a balanced equation. A word equation is just, you're given the names of the reactants and products. Here it says that calcium hydroxide is formed from calcium oxide. How? See, the question is, slaked lime is otherwise called calcium hydroxide. That is formed. So formed means it's a product. I write it on the right side. It's formed from calcium oxide. From means it's a reactant. So my calcium oxide would be a reactant, calcium oxide. Now, what is that something which should react with this to get this product? I have two reactants and one product. Can anyone tell me what is that something missing here which gives calcium?
Water.
Very good. Good. Keep it up. Is it Abdullah? Great. And I guess other participants also you might be knowing, but maybe you don't want to answer, or maybe you're introvert, maybe you're shy. Yes, that is water. Okay. Now the rest is balance it. Balance it. I have one calcium. I have two oxygens, two hydrogens. Oh, it's already balanced. One calcium, two oxygens, this two oxygens, two hydrogens, it's already balanced. Yes. So which of these is the equation? Come on. You can't say which one, 1, 2, 3, 4. Which of these? Okay. Yeah, 2. Good. And the last one, and then the coordinator will speak with you. Okay. Limestone. You know, limestone is calcium carbonate. You call it marble. Marble is calcium carbonate, or limestone is calcium carbonate. Even the eggshell is calcium carbonate. Even the chalk piece is calcium carbonate. All these are sources of calcium carbonate. When I heat calcium carbonate to about 300 degrees Celsius, you know, the temperature is 300 degrees Celsius, you get two substances. When any carbonate is heated, I get carbon dioxide gas, any carbonate, and I get calcium oxide. Calcium oxide is lime powder. You know, just the one we were discussing before. I said calcium oxide mixing with water, you get calcium hydroxide, isn't it? That calcium oxide is also called lime powder. Remember, I'll write here. Don't worry, I'll write here. Calcium oxide. This is calcium oxide. It is a chemical name, but commonly we call it lime or lime powder. But calcium hydroxide, CaOH taken twice. This is calcium hydroxide. This is calcium hydroxide. It's commonly called as lime water. So please be careful. Lime powder is different. Lime water is different. Lime powder is calcium oxide, which I get when I heat limestone. And lime water, when I mix that calcium oxide in water, I get calcium hydroxide. We just discussed this in the second question. This calcium oxide, when I dissolve in water, I get calcium hydroxide. And this calcium hydroxide, I told you the test for carbon dioxide. When I bubble carbon dioxide, when I pass carbon dioxide through this lime water, I again get the same calcium carbonate. So remember, calcium carbonate is CaCO3, lime powder is calcium oxide, and lime water is calcium hydroxide. So this is how you need to understand experiments and analyze the experiments and interpret the questions, tackle the questions. And this is how we teach at Tutopiya, and this is how we discuss the past questions. And thanks for your time, thanks for your patience and the cooperation. And one of our coordinator is going to have a small word with you all for about 5 to 10 minutes, and I'm going to leave my desk. Thank you.